So our final and somewhat brief section is to look at a few things that relate to amines. We don't have so much in terms of reactions to talk about in this chapter. The most important reactions of amines are things that we actually discussed in previous chapters. Amines, of course, are extremely important biologically, as we've talked about many times in the past. Probably nothing more important than being one of the two functional groups that's present in every amino acid. When it comes to amines, you may also recall that we can divide them up into three different categories. Primary, where the nitrogen is bonded to one R group. Secondary, where it's bonded to two R groups. And tertiary, where the nitrogen has three R groups. So we can get into a little bit of nomenclature. And nomenclature of amines is a little bit funny in places because it's a really big mix of common names and systematic names. But we're going to start with sort of the simplest case, which are primary amines. Because primary amines are going to very, very closely follow what we learned for alcohols. So hopefully you recall that we would have named a molecule like this as 2-butanol. The 2 indicating which carbon the alcohol was on, and the ol indicating an alcohol. So if we had an amine that looked exactly like this, that was primary, we would go about the naming in the exact same way that we did an alcohol. We would number it to give the carbon with the amine the lowest possible number, and then we just need an ending to show our amine. And amines have the very complicated ending of amine. So that's how we name primary amines. Basically, it's identical to what we learned for alcohols. So where this gets more complicated is when we get into secondary and tertiary amines. So in many cases, we use what are called what we would refer to as common names. And so for a compound like this, we would name the two R groups. So on this side we have an ethyl. On this side we have an ethyl. So since there's two ethyls, we would just say diethyl and then amine. And you might recall this is very similar to another functional group. How did we name ethers? When the R groups were relatively simple, we used their common names. This one was diethyl ether. So for a lot of amines, we're following rules that we've already learned before, being the alcohol rules for primary amines, and many secondary and tertiary amines look just like ethers. So this being an amine that has 3 methyl groups, we would call it trimethyl amine. And we can do this for amines that don't have all the substituents the same. So this one has an ethyl and a methyl. So we call it ethyl methyl amine. Again, this is very, very similar to what we learned for ethers. If that was an oxygen in the middle, then we would have called it ethyl methyl ether. Now, what happens if things get a little bit more complicated? Well, in a case like this, what we would do is we would use the nomenclature we learned for primary amines to name the longest chain. So that's a 5-carbon chain with the amine on the first carbon. So we would call it 1-pentanamine. And then any other groups we would name as substituents. So that's an isopropyl group. The other piece we have to remember though is how do we number it? We can't give it a number because the numbers in this compound are here. So any number that we would put in front of isopropyl would indicate it's on one of those 5 carbons I've just drawn. So instead we say it's on the nitrogen, and we do that by, instead of a number, we use the capital letter N. So N-isopropyl 1-pentanamine. And that's really the only new thing for amine nomenclature, are more complicated ones like this. Now, even this one, though, isn't that complex, and so it wouldn't have been wrong if we had said we have an isopropyl on one side, a pentyl on the other side, and so I'm just going to call it isopropyl pentyl amine. Alright, so what are some of the important properties of amines? So one thing that they share in common with thiols is a lot of amines have a fairly unpleasant odor. It's not quite as bad as a thiol, but it's certainly not a pleasant odor. But just like alcohols, amines have this, or most amines, obviously this doesn't apply to tertiary amines, but any amine that has a hydrogen, we have a polarized NH bond, just like we do with the OH. Now, amines are not as polar as alcohols. The difference in electronegativity between oxygen and hydrogen is about 1.4, whereas in the amine, the difference is only 3 for nitrogen and 2.1 for hydrogen, so about 0.9. So amines are still polar. They are definitely polar molecules, but the polarization is decreased. What this results in is, if we're again comparing alcohols and amines, the nitrogen has less of that partial negative than the oxygen does. And because the bond is less polarized, the hydrogen has less partial positive character than the H in the alcohol. So overall, amines still can participate in hydrogen bonding, but relative to alcohols, it is a weaker hydrogen bond. As we have many times before, let's illustrate that with some numbers. So we can compare CH3, so ethane, which has no hydrogen bonding, to methylamine, which has the weaker H bond, and methanol, which has a stronger hydrogen bond. So ethane has a boiling point of negative 88 degrees Celsius, whereas methanol has a boiling point of 65 degrees Celsius. Where does the amine fall? Well, the hydrogen bonding is still a significant effect. It's still almost 100 degrees higher than having no nitrogen or oxygen in the molecule. But we can see it's not as significant as having the oxygen. The oxygen makes the boiling point another 60 degrees higher. So where does this put amines in sort of in terms of our grand scheme of functional groups and polarity? Well, it turns out an amine, like propylamine, if we compare that to propanal, an aldehyde, they have, and these are very, very similar molecular weights, that's why we're comparing them, they have almost identical boiling points. And so overall we could rank our functional groups. Ionic, most polar, highest melting points, highest boiling points. Carboxylic acids, alcohols, ketones, aldehydes, and amides are all very, very similar. And then hydrocarbons, alkanes, alkenes, alkynes. What about water solubility? Water solubility follows the same trend as pretty much every other functional group. Very low molecular weight, generally water soluble. Once you get up above 4 carbons, generally not water soluble. So the only reaction that's new that we're going to talk about with amines is just to look briefly at its acid-base properties. So amines because of that lone pair on nitrogen, are weak bases. And so if you add a strong acid to them, you can protonate that amine to form what's known as an ammonium salt. So an ammonium salt is when we have an amine that has a fourth bond to it and therefore a positive charge. And hopefully you recall something we talked about with carboxylic acids. You remember with carboxylic acids that when we had just the acid itself, in general, those, unless they were very small, would not be water soluble. But what happened when the carboxylic acid got deprotonated? It formed an ionic compound, a charged species. And at that point, it became water soluble. Same behavior for amines. Larger molecular weight amines, not water soluble. But once you add that extra hydrogen and you make them into a salt, just like the act of deprotonating the carboxylic acid, at that point, it will very, very often be water soluble. So finally, what are the things that affect base strength for amines? Well, for any functional group, if we're talking about base strength, if we add electron density, such as by adding an electron donating group, then acidity will go up. If we add electron withdrawing groups, which will decrease density, it should make sense logically. If a base is something that's giving its electrons away, but now you start to take those electrons away from the base, it should make sense at that point then that amine is no longer going to be as strong. And so when we add electron withdrawing groups, that decreases electron density. We find that the acidity goes down.